Let's get into it. Number 10. Asteroid impact. You are outside and a streak rips across the sky. For a moment you think it is a shooting star. Then the ground shakes. A sound like 1,000 thunderclaps rolls in from the horizon. A rock just punched through the atmosphere and hit the surface with the energy of millions of nuclear weapons. The impact throws dust and debris kilometers high. Fires ignite in every direction. A wall of superheated air flattens forests for hundreds of kilometers. Near the coast, the strike sends waves taller than buildings racing outward at the speed of a jet. In 1980, Luis and Walter Alvarez found a thin layer of iridium in rocks worldwide. Iridium is rare on Earth but common in asteroids. That layer marked the moment a 10-kilometer rock struck what is now the Yucatan Peninsula and ended the age of the dinosaurs 66 million years ago. We learned from that. NASA catalogs near-Earth objects through surveys like NEOWISE and the Catalina Sky Survey. The DART mission in 2022 proved we can nudge an asteroid off course by crashing a spacecraft into it. For the big targets, we get years of warning. The gap is the middle ground. In 2013, a rock about 20 meters wide exploded over Chelyabinsk, Russia. Nobody saw it coming. The blast shattered windows across the city and injured over 1,000 people. 20 meters. The one that killed the dinosaurs was 500 times wider. Our catalogs cover most of the large threats. The small and medium ones still slip through. A single unseen rock the size of a football stadium could flatten a city and crash global supply lines overnight. But some threats do not need to touch the ground. Number 9. Solar superstorm. On September 1st, 1859, a British astronomer named Richard Carrington was sketching sunspots when he saw two brilliant patches of white light erupt from the sun's surface. He had just witnessed the most powerful solar flare in recorded history. Hours later, the sky lit up with auroras as far south as Cuba and Hawaii. Telegraph systems across Europe and North America failed. Some operators reported sparks leaping from their equipment. A few stations caught fire. That was 1859. The world ran on wires and steam. Today, it runs on satellites, microchips, and transformers that were never designed for a storm of that size. In 2012, a coronal mass ejection of similar scale flew through Earth's orbit. We missed it by 9 days. 9 days of orbital timing separated modern civilization from an event that could have knocked out GPS, banking networks, and power grids across entire continents. The physics are straightforward. The sun ejects a bubble of magnetized plasma. It crosses 93 million miles in 1 to 3 days. When it slams into Earth's magnetic field, it drives massive electric currents through the ground. Those currents flow into high-voltage transformers and burn them out. Each one takes months to build. There are no spares sitting on shelves. Without transformers, the grid stays dark. Without the grid, water treatment stops, fuel pumps go silent, and cold storage fails. The phone in your pocket depends on GPS satellites. Every one of those satellites is exposed. The National Academy of Sciences estimated in 2008 that a severe storm could cause up to $2 trillion in damage during the first year alone, and take 4 to 10 years to fully recover. Space weather centers give us hours of notice. That is enough to shut down satellites and isolate some grid sections. It is not enough to redesign a system that was built fragile. The sun at least gives us hours. The next threat gives nothing. Number 8. Gamma ray burst. The flash arrives at the speed of light. By the time you see it, the damage is already done. Somewhere in the distant universe, a massive star ran out of fuel, and its core collapsed into a black hole. In the final moment, twin jets of gamma radiation shot outward along the star's poles. One of those beams crossed thousands of light years and swept across Earth. The gamma rays do not burn you directly. They work on the atmosphere. High-energy photons split nitrogen and oxygen molecules in the upper air and rearrange them into nitrogen dioxide, a brown toxic gas. That gas destroys ozone. In a matter of weeks, the shield that blocks ultraviolet goes thin. Adrian Mellett at the University of Kansas has spent years modeling what happens next. Ultraviolet that normally gets filtered now reaches the surface at sterilizing intensity. DNA breaks down. The base of the marine food chain, the organisms too small to find shade, dies off first. Malott and his colleagues believe a gamma-ray burst may have triggered the late Ordovician extinction about 440 million years ago. The evidence is circumstantial, but the chemistry lines up. Certain isotope ratios in ancient seabed rock match what the models predict from a burst at moderate range. There is no defense against this. No warning system helps when the danger moves at light speed. The burst is the announcement. Fermi and Swift satellites would record it as a historical footnote, not a forecast. The next threat is quieter. It makes no flash at all. Number 7. Rogue black hole. The stars look normal. Then over months astronomers notice something strange. The orbits of distant objects in the outer solar system are shifting. Something massive is pulling on them, and it gives off no light. A stellar mass black hole, 5 or 10 times the mass of the Sun, has drifted into the neighborhood. These wanderers get ejected from binary systems or dense star clusters and drift between stars for billions of years. Astronomers estimate the Milky Way holds hundreds of millions of them. The Gaia spacecraft has mapped over 2 billion stars with extreme precision. If a heavy invisible object passes between us and a distant star, Gaia can detect the tiny gravitational lensing. That gives us detection. It does not give us protection. A rogue black hole passing through the outer solar system would tug on the Oort cloud, the vast shell of icy bodies at distances 1,000 times farther than Pluto. That tug sends comets inward. Not 1 or 2, thousands, arriving over decades and centuries. A sustained bombardment that no single deflection mission could handle. Worse, the gravitational pull can subtly shift planetary orbits. Earth might drift a fraction closer to or farther from the Sun. A small change in orbital eccentricity alters seasons, ice coverage, and rainfall patterns on timescales that agriculture cannot follow. The danger is not being swallowed. You would need to fly directly into a black hole for that. The danger is having your solar system quietly rearranged by something you never saw. At least a rogue black hole takes months to pass. The next threat announces itself with a flash and then poisons you for centuries. Number 6. Supernova. Betelgeuse, the red giant on Orion's shoulder, is going to explode. Not tomorrow. Probably not for another 100,000 years. But when it does, it will light up the daytime sky for weeks. At 650 light-years away, Betelgeuse is too far to hurt us. The dangerous range is much closer. Mark Reed at the Harvard-Smithsonian Center for Astrophysics has helped pin down the distances to massive stars in our region. The critical threshold is roughly 30 light-years. Inside that range, a supernova becomes a different kind of problem. The kill mechanism is not the light. Neutrino detectors like IceCube in Antarctica would pick up the core collapse hours before the light peaks. That is a genuine heads up. The real threat is what comes after. High-energy cosmic rays, protons, and heavier nuclei accelerated to near light speed, slam into the upper atmosphere and penetrate to ground level. Radiation dose rates rise. Cancer rates climb across exposed populations. Electronics suffer increasing single-event upsets, random bit flips caused by energetic particles punching through microchips. Satellites degrade. Navigation systems drift. A nearby supernova would also compress the heliosphere, the bubble of solar wind that normally shields us from interstellar gas and dust. With that shield pushed back, Earth sits exposed to the raw interstellar medium. Climate models suggest temperature shifts, altered cloud formation, and unpredictable weather for centuries. Less an explosion, more a slow poisoning of the entire environment. The flash is dramatic. The dying takes generations. Some threats work even slower than that. Number 5. Rogue planets. In 2011, astronomers using gravitational microlensing surveys estimated that the Milky Way may contain billions of free floating planets. Worlds ejected from their parent systems, drifting alone through interstellar space. Most pass unnoticed. The concern is a large one. Jupiter mass or bigger, drifting through our outer solar system. The Nancy's Grace Roman Space Telescope will conduct the most sensitive microlensing survey ever attempted, and is expected to find hundreds of these wanderers. A large rogue planet would not destroy Earth by collision. The odds of a direct hit are vanishingly small. The damage comes from orbital mechanics. Jupiter's gravity keeps the inner solar system relatively stable. A sesquipedal mass object passing through would change the gravitational balance that has held for 4 billion years. Earth's orbit could stretch into a more elliptical shape. Hotter summers. Colder winters. A climate that swings between extremes the biosphere has not faced since the Permian. In the worst case, Earth drifts out of the habitable zone entirely, sliding toward temperatures like those on Mars over thousands of years. Slow enough to measure. Not slow enough to fix. You cannot push a planet back into its old lane. The next one is fast. Very fast. Number 4. Magnetar Starquake. On December 27, 2004, instruments on satellites and ground stations around the world spiked simultaneously. Detectors saturated. Data jumped off the charts. Something had dumped more energy onto Earth's upper atmosphere than anything ever recorded from outside the solar system. The source was SGR 1806-20, a magnetar on the far side of the galaxy. Robert Duncan at the University of Texas and Christopher Thompson at the Canadian Institute for Theoretical Astrophysics had proposed the magnetar model back in 1992. This event confirmed what they predicted. A magnetar is a neutron star with a magnetic field roughly 1,000 trillion times stronger than Earth's. When the crust fractures under magnetic stress, it releases a giant flare. This one, in 0.2 of a second, released more energy than the Sun produces in 250,000 years. From 50,000 light-years away, it compressed the ionosphere and disrupted radio signals worldwide. You were probably at work or watching television that afternoon. Most people never heard about it. From 10 light-years, the same flare would have been catastrophic. The electromagnetic pulse would fry satellite electronics and overwhelm power grid protections. Communication networks would cascade into failure. GPS signals would vanish. The closest confirmed magnetar sits about 8,000 light-years away. But magnetars are only visible when active. A quiet one could sit much closer, undetectable until the next fracture. By the time you see the flare, it has already arrived. Light speed is both the announcement and the weapon. The next threat also arrives too fast to stop, but at least you can see it. Number 3. Wandering interstellar object. In October 2017, astronomers at the Pan-STARRS telescope in Hawaii spotted something unprecedented. An object tumbling through the inner solar system on a hyperbolic trajectory, not boson to the sun. It came from somewhere else entirely. They named it Oumuamua. It was already on its way out when they found it. At its closest approach, it had been moving at roughly 26 kilometers per second, peaking near 88 kilometers per second as the sun's gravity slung it through. A rifle bullet travels about 1.25 kilometers per second. Oumuamua was moving 70 times faster. Comet Borisov followed in 2019. A third visitor appeared in 2025. Models now suggest thousands of interstellar objects pass through our solar system at any given moment, undetected. This is the hole in planetary defense. Everything NASA has built assumes the threat is a local rock on a predictable orbit that we can track for years. The DART mission, the NEOWISE catalog, the Catalina survey, all of it requires time. An interstellar object comes from a blind spot at a speed that makes deflection meaningless. There is no window to design a mission, build hardware, and launch. Impact energy scales with the square of velocity. An interstellar rock the same mass as a local asteroid but moving 4 times faster hits with 16 times the kinetic energy. We would see it. We would calculate the impact point. We would not be able to stop it. That is a rock. The next threat forges gold. Number 2, neutron star collision. The gold in a wedding ring, the platinum in a catalytic converter, the uranium in a fuel rod. All of it was forged in the same kind of event. When 2 neutron stars spiral together and merge, they create what astronomers call a kilonova. The collision reaches temperatures so extreme that nuclear reactions build elements heavier than iron in seconds. In 2017, the LIGO and Virgo gravitational wave detectors caught the signal from two neutron stars merging roughly 130 million light-years away. The observations confirmed what Stefan Roswag at Stockholm University and others had modeled for years. The merger ejects a cloud of radioactive heavy elements at a significant fraction of light speed. That cloud glows for days as the unstable isotopes decay. At 130 million light-years, it was a scientific triumph. At 30 light-years, it would be an extinction event. The merger produces a focused jet of gamma radiation. If Earth falls in that beam, the pulse triggers immediate electromagnetic disruption on a global scale. But the part that separates a kilonova from a simple gamma-ray burst is the ejecta. Radioactive debris expands outward. At close range, it reaches the solar system and seeds the environment with short-lived isotopes. Radiation levels rise not from the sky, but from the ground, the water, the dust you breathe. Fallout, not from a bomb, but from a collision between dead stars. Gravitational wave detectors give seconds of notice before the final merge. The gamma jet arrives at light speed. The ejecta follows over years. The first sign something is wrong is radiation monitors climbing with no obvious source. No merging pair currently threatens us. The galaxy holds an estimated 100 million neutron stars, and we have mapped a tiny fraction. The next merger only needs to happen close once, and then there is the one that does not come from any star, any collision, or any object at all. Number 1. Vacuum decay. This is the one that frightens physicists. Every atom in your body holds together because of the Higgs field. That field gives mass to the fundamental particles that make up matter. In 1964, Peter Higgs and several other theorists proposed its existence. In 2012, the Large Hadron Collider at CERN confirmed it by finding the Higgs boson at a mass of 125 billion electron volts. That number matters. It places our universe in what physicists call a metastable state. The Higgs field is not at its lowest possible energy. It is sitting in a shallow valley with a deeper one below. Stable for now, possibly stable for trillions of years. But not guaranteed. A random quantum fluctuation anywhere in the universe could nucleate a bubble of true vacuum, tiny region where the Higgs field drops to its real minimum. Inside that bubble, the constants of nature change. Atoms cannot form. Chemistry does not work. Matter as we understand it becomes impossible. The bubble wall expands outward at the speed of light. You cannot detect it before it arrives because nothing outruns it. There is no signal, no flash, no warning. One moment physics works the way it always has. The next moment it does not. You would never even process the transition. José Ramón Espinosa at the Institute for High Energy Physics in Barcelona has run the stability calculations. The expected lifetime of our vacuum state may exceed 10 to the power of 100 years. A number so large it makes the current age of the universe look like a rounding error. But this is the only threat on this list with no defense. Every other phenomenon leaves room for preparation, deflection, or survival. Vacuum decay leaves nothing. No shield. No bunker. No warning. If it begins, the story ends. Not just for Earth, for everything the bubble reaches. Forever. The odds are nearly zero. The stakes are everything. Some of these threats are fast. Some are slow. Some give you hours. One gives you nothing at all. The question worth asking is which kind you would rather face.